Are you on?
So the first session of the conference is on theoretical aspects of quantum simulation algorithms. And we're very happy to have our first speaker, Aram Harrow from MIT, who's going to talk about randomized state-dependent Hamiltonian simulation. So take it away. And I think it's around 35 minutes plus time for questions.
Great. Yeah. So thanks to the organizers for inviting me. It's exciting to be here. I am going to tell you about two works in progress with one project with Angus Lowe and Freek Vitaven, and another one with Mintron and Alexander Zlokapa. Both of those two are actually going to speak later today about different projects, so we'll be overrepresented today. Theirs are actually much more complete than what I'll tell you about today. I'm going to tell you about something that's really, we have some results and is still awaiting a full evaluation. But it's work I find pretty exciting, and I'm happy to share it with you. So, if I were to think about like what is one of the themes of QSim, it's that we're all taught certain lies. Maybe a Eurocentric view of American history. But today, the big lie we're taught is quantum simulation is already solved. Like Feynman pretty much nailed it, and then Seth Lloyd showed you could do it in polynomial time, and then higher order Trotter really nailed it. But we find that like even when it's solved completely optimally, there's still more room for progress, and actually there's quite a bit of room left to go, right? And so I'm going to try to revisit some of the things that we areas of quantum simulation where you think it's already optimal, but there's quite a bit more room for improvement. And then another maybe more specific thing that a lot of people believe, I certainly believed until a few months ago, is, okay, entanglement's complicated, multipartite entanglement is terrible, mixed state entanglement is a mess, but there's just the only thing that's good about entanglement is pure bipartite entanglement. Like at least that we can understand. We have the Schmidt decomposition, everything about it you can write down in closed form. If you want to truncate, if you want to approximate it with something that's less entangled, we know how to do that. You just keep the top Schmidt values. And it turns out even that sort of basic fact that we thought we knew, or at least I thought I knew, turned out not to be true. So I'm going to start off by telling you about that, and then I'll discuss the connections to quantum simulation. So here's a classic problem, simple enough to fit on one slide. I have a pure state. It has a Schmidt decomposition. I've already put it into the Schmidt form. I'm going to make the coefficients non-negative just to make life simple. And let's say the Schmidt rank is D, and I want to squish it down to something with a lower Schmidt rank, like K. So what should we do? I mean, you're probably at this point nervous about giving an answer to that. But a reasonable answer is to just take the top K Schmidt coefficients, right? It's a very reasonable thing to do. And the fidelity you get, here's the definition of fidelity I'm going to use. I mean, it's like the inner product, not the squared version. The fidelity you get is basically the norm of that top part of the state, right? The whole state has norm 1. You throw away the little parts, and then you're left with something with less norm, like 0.99, and then that's the fidelity. Pretty straightforward, pretty clear you can't do better. An even simpler version of this problem is instead of having two systems, I just have one system. It's one qdit, and then it still has these coefficients v1 through vd, non-negative. And I want to approximate it now, not with a state with low entanglement, but with something with a sparse vector, meaning it has only k non-zero entries. So this is pretty closely related to the previous problem. And again, there's a pretty obvious answer to if you want to maximize the fidelity. You just have to take the top k entries and rescale it to make a unit vector, and that's the end of the story, right? So I kind of enjoy this problem because there's such an obvious answer. And even when you look at other metrics, it doesn't seem to change things very much. So here are a few other metrics that you might look at. The first one is fidelity. We've talked about that. What about trace distance? Trace distance, you could say fidelity to tests is trying to say how well will you do if someone comes along and tests, are you exactly the state I'm looking for or an orthogonal state? Fidelity will tell you how likely you are to pass that test. Trace distance will tell you about an arbitrary test, right? How much will the probability shift, or how much will the expectation value of an observable shift for an arbitrary test? It's this Schatten 1 norm. But for pure states, those are more or less the same thing. There's this tight relation between fidelity and trace distance that their squares sum to 1, kind of like sine and cosine. So if you know one, you know the other one. Optimizing fidelity is the same thing as optimizing trace distance. There's no daylight between them. There are other measures you might imagine as well, but they don't tend to not work very well for pure states. For example, one metric is the relative entropy, sort of a measure of asymptotic distinguishability. But if you have two pure states, the relative entropy is a very boring number. It's either 0 if they're equal or infinity if they're not equal. So there's nothing really to optimize. Either the state has sparsity k in the first place, and there's nothing to do, you just get it exactly, or it doesn't, and then you incur some non-zero error, which is infinity under this metric. So it's not really a useful metric for pure states. A similar one, people call it D max, or max relative entropy. It's also called the robustness, with a different, if you measure it in a different way. And it's basically saying, if I have the true state V, and I'd like to approximate it with the state sigma, then what is the smallest number I can put in to make this operator inequality true? Okay? So if V is equal to sigma, then e to the lambda can just be 1. And if not, then maybe this will be true with some bigger number. Like if I take sigma to be maximally mixed, then this will be true if I put in the dimension, right? So for a big enough number, you can make this operator inequality true. But again, it doesn't work for pure states, right? It can only work for approximating something relative to a mixed state, not relative to a pure state. So it turns out that the reason why we got such a simple answer about approximating with something sparse is because we had restricted ourselves to pure state approximations, which is kind of reasonable. You started with the pure state. Your goal is a pure state. So shouldn't you approximate with the pure state? You know, bring yourself closer to the goal. Why add noise if nobody asks you to? Well, let's consider the possibility of using a mixed state approximation. And this is the first part of the project I'll talk about with Angus and Frake. So let's suppose our goal now is to approximate our vector with a mixed state, and I don't want to add any resource other than randomness. So before I was allowed to use k sparse vectors, meaning things that are superpositions of only k terms. Now I want to allow things that are just mixtures of k sparse vectors. Okay? So now let's see how things look. Well, if you're trying to optimize fidelity, then changing to mixed states doesn't change very much. The square of the fidelity is just linear in sigma. And so if you're trying to optimize a linear function, you might as well just go with one of the extreme points. You might as well go with a pure state. Maybe a mixed state could do as well, but it'll never do better. So let me try and calibrate things. I'm going to call in pretty much from now on, I want the fidelity to be square root of 1 minus epsilon. So that'll be kind of our benchmark, and then we'll see how everything else measures relative to that. So if you can get a pure state with fidelity square root of 1 minus epsilon, that's also the best you can do with a mixed state. Okay? So again, you know, this idea that the best you can do is take the top K-Schmidt coefficients is seems like a reasonable idea. But for trace distance, it's another story. In general, the trace distance is, for mixed states, no longer tightly related to the fidelity. It can be off by up to a square root factor. So if the infidelity is, I put square root of, oh yeah, if the fidelity is root 1 minus epsilon, then the trace distance you get is square root of epsilon, and it turns out that's the worst possible trace distance, given that fidelity. You could in principle, get the trace distance as much as quadratically lower, and in some cases that's possible. And so if you consider other metrics like trace distance, it's possible to improve. And of course, for relative entropy, here I don't actually know the answer. I just want to raise this as a question. It's certainly true that for relative entropy you can do better, because you just have to beat infinity. I don't have actually the right answer to this, but I know there's improvements. And for the max relative entropy, I do have a formula. It doesn't fit into this box. I'll present it later, but there is an exact formula. The answer is definitely better than infinity, something efficiently computable, and so on. So with mixed state approximations, you can do much better. You can do anywhere from a little bit to much better with mixed state approximations. So I'm going to discuss this in terms of some examples. Maybe I'll pause now. Are there any questions about the setup, about what kind of problem we're considering? So let me illustrate what I'm talking about with a few examples to see, what kind of improvements might you get. So here's a very simple example. Suppose your state has coefficients root 1 minus epsilon and root epsilon. And so there's the pure state, there's the density matrix. And so this is already too sparse. So the only way to compress it is to make it one sparse. And so here's a little diagram, one big value, one big amplitude, one little one, and you want to just keep one of the amplitudes. Very simple truncation problem. And so what can you do? Well, if you want a pure approximation, it's extremely simple. One sparse vectors, there's not many choices. It's either ket 0 or ket 1. Pick one of those. And obviously ket 0 is better. So the best pure approximation is just this 1, 0, 0, 0 density matrix. The fidelity is always going to be root 1 minus epsilon. I've just kind of calibrated things that way. The trace distance is root epsilon. For all pure states, that's how it works. And the robustness, that's this comparison between, this quantity right here, this e to the lambda, you could also call this 1 plus robustness, is of course infinity for pure states. For mixed states, it's still very simple. You're just allowed mixtures of 0 and 1. That basically means diagonal density matrices. And so if you want to get the best fidelity, you should actually go with the pure approximation, right? We saw that's true in general. But if you want the best trace distance, you should hedge. You should output something, this mixture of 1 minus epsilon and epsilon. So what's going on here, you can see a little bit already with this example. Suppose you're a weather forecaster and you think it's going to be 80% chance of sun, 20% chance of rain. You could, for your forecast, just say sunny, right? And you have that maximizes your chance of being shown to be correct. Or you could say for your forecast 80%, 20%, right? There's sort of the two views of how you should answer that question. Either trying to just get the most likely answer or try to get the range of outcomes. And so what this mixed approximation does is it tries to get the range of outcomes. It does so by sacrificing some fidelity, right? You have this, you output this second outcome, ket 1, with probability epsilon, which most of the time is going to be wrong. So from a fidelity point of view, you lose out. But you improve the trace distance, and you improve the robustness. So this example, it actually doesn't look so good for the picture, right? Because the trace distance only improves not to leading order, whereas the fidelity does suffer. So this paradigm, it helps you in some cases. It doesn't always help you dramatically. But an example where it helps you a lot more is when you go to 3 dimensions. And in general, when you allow 2 sparse approximations. So here, let's suppose your state is root 1 minus 2 epsilon, root epsilon, root epsilon. So here the coefficients look like one big amplitude and two little ones. Again, we're going to keep two of them. So here's the density matrix. And now the situation is, the range of what you can do with mixed approximations is a little more interesting. If you look at this density matrix, okay, so the best pure approximation, you have to pick something too sparse, which means you only, you have 0, 1, and 2, and you have to pick two of those. You should definitely pick 0, and then you're indifferent between choosing 1 and 2. So if you pick whatever you do, you're going to get some 2 by 2 subblock correct, and you'll miss out on the rest. And so if you look at these off diagonals, all these square root of epsilons in the off diagonal, you're going to miss some of them. And so that means that you're going to incur a trace distance on the order of square root of epsilon. Whereas if you allow mixed approximations, you don't have to do that. You can do something like superposition of 0 and then either 1 or 2 randomly chosen. What I'm writing down here, by the way, is not the exactly optimal thing. There are these, if you want to make it optimal, you would have some, it would just be more annoying to write down. Okay, what I'm showing you is something that's optimal to leading order. That basically gets you the right leading order scaling. There is a formula for working out the optimal thing, which, yeah, I just didn't want to make the slide too messy. So what does this achieve here, this mixed approximation? So the fidelity is on the same order as it was before. Before it was 1 minus order epsilon. Now we maybe have a worse constant in front of the epsilon, but it's still 1 minus order epsilon. But in terms of trace distance, all those square root of epsilon off diagonal terms, we've nailed those, right? We've gotten all the square root of epsilon stuff right. The remaining trace distance errors are in the order of epsilon. So we have nearly a quadratic improvement in trace distance in this example. And of course, robustness, it's very easy to improve on infinity, and we do get a big improvement there too. So in this example, two sparse approximations we can do much, much better with. Okay, here's something a little more asymptotic. Suppose you have the qubit version of a maximally entangled state. So just all the amplitudes are 1 over root d. If you want to get fidelity, and I'm trying to calibrate to fidelity of root 1 minus epsilon, if you want to get there, then you have to keep most of the entries. So you're going to keep a 1 minus epsilon fraction of the entries. So here you have got a lot of little amplitudes, and you keep, d times 1 minus epsilon of them. So how did this do in terms of performance? Well, all the pure approximations are pretty much as good as any others. Pick any k, and you'll get fidelity of root 1 minus epsilon, trace distance of root epsilon, infinite robustness. Those are kind of, it's always the same, right? For all the pure state ones, it's always the same. For the mixed case, what you should do is average over all of these, and then here things are quite good. The fidelity stays exactly the same, and the trace distance improves by nearly a quadratic factor. For similar reasons to the last example. Basically, if you just take a pure state, you just completely miss most of the off diagonals. You nail some of them, maybe not most of them. You completely miss a significant number of the off diagonals. And if you do a mixed approximation, you can get at least some weight on all of the off diagonals. And the remaining error is order epsilon instead of square root of epsilon. And the robustness is also a pretty good number. On the other hand, not all examples have big improvements. So if you want to show an example where this does badly, you can take maybe the first k of the amplitudes will be big, and then you have a long tail. So this is an example where you're not really indifferent between many different pure approximations. There's one clearly best pure approximation, and to deviate from that will cost you a lot. And so it's harder to find room to mix over many things. And Indeed, that's what we find when we look at mixed approximations. The best mixed approximation is basically still doing the pure state. And that's true for trace distance at least. For robustness, you have to do something a little bit different. For robustness, you can't use a pure state. And it turns out the robustness is quite large. It could be as much as d epsilon. To be generous to this example, you could say, well, I've tuned it so that we're allowed to have it be k-sparse. And I've tuned this state so that you just need to spend all k of your entries on the first k amplitudes. What if you allow 2k amplitudes? This is something in the classical optimization literature that people call a bi-criteria optimization. To say, instead of competing with the best k-sparse, I'm competing with the best k-sparse pure approximation, but I'm going to allow myself a mixed 2k approximation, right? A still similar order of resources. Can I then get a quadratic improvement? And even there, I can't quadratically improve the trace distance. I can make the robustness a good deal better, but still it's fairly large. So what I hope you take away from these examples is this is something that does not always achieve a quadratic improvement in trace distance. It sometimes does. It always makes the robustness finite. Sometimes it makes it a number that's on the order of the infidelity, but sometimes it can be bigger. Okay? So I think a natural question is, okay, why is he just showing us a lot of examples? Where's the formula? Yeah, here I have some good news and some bad news. Let's talk about finding an optimal approximation. This is a well-posed convex optimization problem. That's the good news. So the first thing we like to do is write down a convex set. This is the set of approximating of the states that we're allowed in our approximation. So we start off with some pure state that's our target, and then we have this convex set of things that we're allowed to use to try to get close to it. This has been studied in the resource theory literature under the name of k-incoherent states. So there's a lot of literature on trying to give a resource theory of thermodynamics or things like that. And in the course of doing that, they've said, what if coherence is a resource? And so what if the k-incoherent states, they're called, are free, then what is the cost of other states? And so what this means is just mixtures of k-sparse pure states. We'll call that I sub k. And so then you have a picture kind of like this. Should have made that line thicker. You've got this thing that's not quite a polytope. It's like a polytope with like rounded sides. And then your pure state is outside of it. And you want to find the closest point in I sub k to your pure state. And as we've seen, closest can be defined in several different ways, right? Fidelity, trace distance, robustness, etc. Classic convex optimization sort of problem. The bad news is just because it's convex doesn't mean it's easy. Kind of like the separable states, it's a convex set, but optimizing over it is NP hard. And optimizing a linear function over a set is more or less equivalent in difficulty to testing membership in the set, so that's also NP hard. So if I have a mixed state saying, is this thing a convex combination of k-sparse states? NP hard question. If I have an observable and I say, I'd like to maximize the expectation value of this observable over k-sparse states, NP hard question. And it's NP hard when k is growing, right? If k is fixed, then this is the size of this whole thing is like d to the k, because there are just not that many different subsets you can do. So there's sort of for small k, this is a reasonable thing. But if k is growing with the dimension, then this is something where the complexity is growing. Okay, why is this hard? There's a very simple argument. Let's consider maximizing a linear function over this set. So think about an observable. And I want this observable to be A, the adjacency matrix of a graph. Okay, so I have an undirected graph. I have a matrix A that puts a 1 wherever there's an edge and a 0 otherwise. And then I want to compute this little optimization problem, maximum of A, trace A times sigma, where sigma is one of these mixtures of k-sparse states. Now, this is linear in sigma, so I might as well just take sigma to be pure. This gets the same optimum. And so I'm just maximizing, I'm sandwiching A, I'm taking the expectation value of A relative to a k-sparse state. And that basically means restricting A to some subset of k rows and columns, and then taking the top eigenvalue of what's left. And so in graph terms, that means take a subset of k vertices and look at the subgraph there, and look at the norm of the adjacency matrix there. If those k vertices are fully connected, if they're a clique, that norm is going to be k minus 1, because you've just got a matrix where the diagonal is 0 and everything else is 1. And if it's not a clique, the norm is going to be something less than k minus 1. So if you can distinguish those two cases by computing, say, this quantity, then you can figure out if the graph has a k clique or not. And so if k is a parameter that can grow, this is a classic NP-hard problem. And it's one of the bad NP-hard problems. Like, it's hard for random instances. It's hard to approximate. The sum of squares algorithms fail dramatically on it. My first plan for this, by the way, was to like work through the Hamiltonian stuff and then walk over to the computer science, get a well-posed optimization problem and walk over to the computer science department, and they would tell me the state of the art on it. And all of that worked. They just gave me a bad answer. Okay, so but don't worry, the talk's not over. I have some more things to say. So you can do some things. So what can we figure out? There are some glimmers of hope from the computer science literature that we can use. There's a way of thinking about this in terms of norms, where we can compute some useful things. So first, let me define a pretty simple norm. It's kind of the one we've been looking at from the beginning in terms of fidelity. It's called the top k norm. For when people talk about the singular values of matrices, they might call this a chi-fan norm. This top k norm might have other names too, which I can't remember right now. But it's basically, you have a vector, you take the top k entries, and you take the Euclidean norm of that. Okay? So I'm going to write this as like a subscript k in parentheses. Operationally, of course, it corresponds to the fidelity, or more precisely, the best possible fidelity with a k-sparse state. It's this kind of benchmark we've been using the whole time. We've always been considering states where their fidelity with the top k, where the norm of the top k entries is √1 minus epsilon. You can also think of this geometrically as k interpolates from 1, just taking the top entry, up to d, taking all the entries. This norm is interpolating between the infinity norm, which is the biggest entry, and the Euclidean norm, the 2 norm. So we can also look at the dual of this. And this is from this machine learning paper from about a decade ago. We'll call this the k-star norm, or the k-support norm. And by dual, what I mean is it's the k-support norm of V is the largest possible inner product I can get between V and something whose top k norm is at most 1. So that's just the classic definition of a dual norm is if I inner product with something whose top k norm is 1, how big can I get? So for example, the dual of just the biggest entry would be adding up all the entries in the vector, the 1 norm. Another way of looking at the k-support norm is if I write V as a sum of vectors W alpha, and each one is k-sparse, what is and I have to pay a cost, which is the sum of the lengths of all of these vectors. What is the lowest possible cost? So in other words, if V is already k-sparse, the norm is just the Euclidean norm. But if not, I have to write it as a sum of k-sparse things, and I have to pay the price for doing that, meaning of adding up the lengths of all the vectors along the way. So these are two equivalent definitions of the k-support norm. You can also think of it geometrically. So remember, the top k norm is between the infinity and the 2 norm, and the k-support norm is between the 1 norm and the 2 norm. So top k norm is less than 1 if this is a unit vector, and the k-support norm is going to be greater than or equal to 1. And it turns out this also has a nice operational interpretation. It just tells you the robustness. It's 1 plus the robustness. This is this thing that goes into the operator inequality. Remember, you have the state we want, ket v bra v, less than or equal to 1 plus r times the approximating state. You can calculate 1 plus r just by calculating this k-support norm. So this norm is basically the answer we're looking for robustness. So this is good news, and there's better news coming up. If you look at these definitions, well, it's like, okay, well, that's a nice formula, but it's not, the way it's written is not efficiently evaluatable, right? Like I have to do a maximum over this scary set, or here I have to minimize over all decompositions, and it seems like there are a lot of possible decompositions. But it turns out there's an efficiently calculable formula for this as well. So let me just recall, this is the top k norm. And this is due to work by Johnston, Lee, Plosker, Poon, and Regula, who are studying this in the context of the resource theories. So the k-support norm is this maximum inner product with anything with top k norm at most 1. And I don't want to dwell on this formula for too long. The key thing that I want you to see about it is that it is a formula with no dot, dot, dots. It just fits in the slide. It's just like has things like plus and divide and sum that you can do on a computer. Maybe I'll say a little bit about what this formula is. If this were just the Euclidean norm, I would just add up all the VI squares. For the top k norm, I'd add up the first k of them. But what this does is it kind of interpolates between the 1 norm and the 2 norm. It goes up to k minus some number r minus 1, doing the squares of all the entries. And then it switches over to this sk minus r thing. And sk minus r is just you add up linearly the 1 norm, just add up all the entries of the remaining entries. So for a while, you're squaring all the entries and adding them, and then you just add up the entries and then square them, which can give you, of course, a much bigger number. And then you divide that by r plus 1. So r is this parameter that governs the point where you jump from doing this 2 norm-like thing to this 1 norm-like thing. And it's just some integer between 0 and k, so there are not very many different values of r to check. So it's efficiently checkable, and this gives you the exact formula for it. This also tells you, so not only do we know the robustness, the number, the quality of the approximation, we also would like this to be constructive. And we can find a construction. This is governed by this parameter r. R basically tells you the top, some number of entries. You should just keep those in deterministically. Those are so big, just like the 1 minus epsilon in those examples. They're so big, those have to go in. And then the remaining entries will importance sample those. So the remaining entries are going to be some zeros, a bunch of zeros, and a bunch of alphas. Alpha is just this constant that's the same for all these non-zero entries. And you put it in with a probability that gives you the right answer and expectation. So if your target was a big amplitude, you put in an alpha with a high probability. If your target was a low amplitude, you don't put in an alpha very often. So that's basically the idea there. Something like this was proposed in the context of tensor networks almost 10 years ago, but without, it was sort of a heuristic it was not exactly this ensemble. It was sort of, I won't get into it. It was a related idea appeared there. So this tells you how good the approximation is and how to achieve it. So let's revisit this table. So now we can fill this in. We can say for the mixed optimum, the robustness is going to be given by this norm. This is an upper bound on the relative entropy and the trace distance. It does not exactly give us the trace distance. For the trace distance, right now we just have upper and lower bounds, which I'm not going to report because they're messy. But that's something that we're still working on. And relative entropy, we really have no idea. So hopefully someone here will have an idea about that. OK, so I next want to talk about some applications. I've heard this conference is about simulation, so let's see how we can use this for simulation. So the first, OK, I know the conference is QSim, but I'm going to talk about classical sim, C-sim-Q. So if you want to simulate a quantum system classically, I mean, it's worth knowing if you're a quantum simulator, you have to know your enemy, right? So I've just given a little more ammunition to the enemy. What you want to do is a matrix product state. So if you have n q dits, and you're going to approximate it by something with rank k across any cut, then this is a matrix product state. And you can get it by doing repeated Schmidt decompositions. And you can use this for DMRG type algorithms by repeatedly optimizing these local tensors. And you can also use it to simulate time evolution. The way you do that is you start with an MPS approximation. You evolve for a little bit, which creates more entanglement. And then you truncate. So that creates maybe more entanglement than you ultimately want to keep. And then you truncate the bond dimension back down to an affordable size. And so the techniques that I've showed you give you a better way of doing truncation. Better if your goal is trace distance or robustness as opposed to fidelity. I forgot to say, by the way, another way of viewing robustness is as multiplicative error. So the trace distance tells you the biggest additive error you'll get with respect to any norm 1 observable. The robustness tells you the biggest multiplicative error you'll get with respect to any PSD observable. So the true answer will be at most, will be at least, 0.8 times whatever the output of your approximation was. That means you get a good multiplicative approximation. So these techniques improve turning a single bipartite pure state into something of lower Schmidt rank. So they also apply to MPS algorithms when you need to truncate. The result, though, is that you do get a randomized truncation. So you have to repeat it a few times in order to estimate things like the variance. But the error that you get will be lower than you'd get from a deterministic truncation. So this is something that we're still pursuing. I suspect also deterministic truncations, by throwing away the small Schmidt values, might also bias you away from what you'd expect in time evolution. In time evolution, if you start growing some amplitude from 0, then that amplitude will be punished by a deterministic truncation in a way that randomized would not punish you. That's just a guess, and that's something that we're going to look at with numerics. But I'm hopeful it'll be better in that sense. OK, what about Hamiltonian simulation? So let's suppose you want to do e to the minus iht. H will be some sum of beta j hj. Each hj is norm 1. The betas add up to 1. OK, so one thing you can do is Trotter. But obviously, we don't just do first order Trotter anymore. One better thing is Q-drift, where you importance sample the entries, and you do each one for the same amount of time. Right? There's this delta coefficient in front, and all you vary is the probability. And Q-drift can be viewed as an example of approximating a big superposition with a sparse superposition. So let's just look at this to first order in T to see what I mean. So to first order in T, your time evolution is going to give you this state. You start with psi, and then you get this minus IT, sum of all the HJs applied to psi. Superposition over many, many states, order L, about L plus 1 states. And then I want to approximate it by a mixture of 2 sparse states. So just superpositions of alpha and a single one of the HJs acting on it. And this is something where the basically turning the crank on that optimal robustness approximation recovers something very much like Q-drift. It recovers the fact that you importance sample the elements and that you do them each for a constant amount of time. It doesn't tell you how to choose the time, but once you fix T, then it tells you the rest. And I should probably wrap up. So let me just briefly say, because I think I'm pushing time. In general, what you can do is, here's your Hamiltonian. You want to pick some random vector u. I should have said that u should be sparse, and evolve according to some linear combination of the HJs. So this is how you might generalize beyond Q-drift, so that instead of picking single Hamiltonian terms, you randomize over small blocks of terms. The u's should be unbiased, or this is what importance sampling does, so that u's should average to the true beta. And then for the second order terms, you want this matrix to be small, and small with respect to various norms. I don't want to get into that, but that's the kind of thing that you want to minimize. And again, you can see this is more or less the problem that we've just been studying, where you have the true vector beta is all entries are non-zero, and then you want to approximate it by a mixture of sparse things. This also can work in a state-dependent way. So if you're starting with the state psi, then first you want to get it to be unbiased. Sorry, there should have been average over u here. I forgot this. We want to average over these u's, and then you want to get the right thing for your first order terms, and then again you want the second order terms to be minimized. And this state-dependent simulation is something where our framework gives you a natural thing to try, and right now we're working on evaluating the effectiveness of it. To do this, I guess the one thing I'll say is the data you need for this is this covariance type matrix of expectation of pairs of terms. This is something that can be readily measured if you're willing to repeat many, many times. And then you can optimize a Hamiltonian simulation based on these. OK, so let me just wrap up, and I'll say these techniques show that to really get the best performance of simulation, we need to randomize. Even if you want to approximate a superposition over many things, the best way to do it involves judicious use of randomness. We can get improvements by doing state dependence, replacing the norm of the operator with the norm of how it acts on the state. And there's a role for classical optimization by doing things like optimizing over these sparse approximations. There are many other things we didn't optimize. Of course, you have the rest of the week to hear about that. But I think it'd be exciting to combine this with things like freedom of how you choose a Hamiltonian. This comes up in chemistry problems. And combining, for example, these quantum simulations with classical tensor network simulations and with quantum Monte Carlo. Other work has done that, and I think there's a role for that here as well. But let me stop and take any questions you have.
Great. So we have time for a few questions.
Who has a microphone?
If you could speak in the...
Hey, Aram.
Hi, Nathan.
Hey, great talk. So one question that I guess two related questions that I've got. First, when you're taking a look at this, looking for a pure state approximation to the mixed state in general, I don't know, that to me it feels like it's underestimating your uncertainty in the resulting target because you're always returning something with zero von Neumann entropy. So is there some kind of information theoretic way you can think about it? And I guess the second related question that I'm kind of curious about the whole paradigm is if you're interested in taking a look at, say, some observable, like, you know, some tensor product of Pauli operators, what you're probably most interested in is you're probably interested in the reduced density matrix that operator acts on. So then wouldn't it actually be more of for an observable dependent way, a mixed state comparison rather than a pure state mixed state?
Great. So wait, say the first question again.
Doesn't having a pure
Oh yeah. Oh sorry. Yeah. Okay. Sorry. Yeah. Okay. Great. Yeah. Two very good questions. Let me also mention, by the way, our randomized Hamiltonian simulation has some relation to the nice composite QGIF work that Nathan and his group have done. So with regard to, you know, what Nathan says about tomography is a point that I remember first hearing from Robin Bloom-Cahoot a very long time ago, which is this idea applies for state tomography as well. Like if I'm measuring some system and I want to say what's my guess for what this qubit, this mixed qubit is, then maybe instead of doing, you know, there are different estimation strategies where I might try to minimize relative entropy, where even if the state is pure, I'm going to output some mixed state. So definitely this issue arises in tomography for sure, and it's and classical tomography as well. Then as for like what is the right metric, it's a good question what the right metric is. I would argue that mixed state, you know, just looking at marginals should not be enough. Of course, at the very end, when you measure, you want the marginals then. Hopefully, for the quantum simulation to be interesting, at some point, you should have been sensitive to some kind of global, some many-body Pauli string. If local things suffice the entire time, that would be kind of bad news for the quantum simulation, I suspect. This is a fuzzy statement. I should mention another one of these previous works was this partially random trotter by Jin and Lee, and they looked at this mean squared error criteria, which I think is another very good way of looking at things. So the question of the metric, it's quite a good deal more complicated than just fidelity, trace distance, and robustness. So yeah, what I said was really just the starting point, and there's quite a bit more room for looking at different metrics based on applications, absolutely.
Okay, great. I think we should move to the next speaker. So let's thank Aram again.